Okay, good afternoon. It's good to be here in real. So welcome to the next Tuesday seminars of the Observatory of Warsaw. And today we have a privilege to host, at least virtually, Richard Andreson, who was actually he has visited us many years ago, and now he's a distinguished fellow in Switzerland. And is very busy, but I hope we will make it up, and Richard will visit us someday soon. But he has been a collaborator on the variable stars and Gaia and all those stuff in the recent years. So Richard is now he's a fellow at the EPFL in Switzerland. He also has an ERC grant. Previously, he has obtained his PhD in Geneva and in astrophysics. Then he moved to Johns Hopkins, where he worked with Adam Rees, and then he was ESO fellow. So he has quite a bright career after him and before him. So Richard is going to tell us about his attempt to measure Hubble constant with 1% accuracy. Richard.
Thank you very much, Łukasz, and thank you very much for being here today, online and in real life, of course. I apologize very much for not being able to make it in person. In this particular case, didn't even end up being due to professional, but due to personal reasons. Really, I apologize. It would have been a pleasure to be there in person. Nonetheless, I'm really honored to be invited to give this colloquium today at Warsaw Observatory. I see Copernicus looking at me very sternly and making sure that everything I will tell you today will stand the test of time, hopefully. So I'd like to just shout out the European Research Council and the Swiss National Science Foundation for funding this research. That's, of course, extremely important for me to do that. So today I'll tell you about how we measure the Hubble constant using standard candles, and in particular, how and why we want to measure this with an accuracy of 1%. And I imagine that many of you are familiar with these concepts, but nonetheless, I find it useful to remind ourselves what we're really dealing with. So as a very sort of broad introduction, the term standard candle, what does that really refer to? Well, a standard candle is any object whose true luminosity, here in the capital letter L, you can calibrate empirically. You can, of course, also know it from a stellar model, but for distance measurements, it's the empirical calibration that counts. And a standard candle will allow you to measure distances because the observed flux F diminishes as the distance squared. That's just because the flux is distributed over increasingly large spherical surfaces. And this ability to measure so-called luminosity distances is really fundamental for all of astronomy, as well as cosmology. And if you will, astronomy, the most basic problem in some sense really is distance. That's because if we're looking at any scene in the sky and we want to see, well, what are we dealing with in terms of what the objects are, distance will help us understand the nature of that source. For stellar physics, it's incredibly important to determine luminosity from observed fluxes because stellar models tend to predict luminosity as a function of mass, metallicity, rotation rates, overshooting, mass loss, and what have you. If we're looking at the Milky Way structure, and of course there's been some work done at Warsaw Observatory specifically on this, distance tells us the structure of our Milky Way, how warped it is, how flared it is, where the spiral arms are located, and so on. But also how ordered are the dwarf galaxy systems in the local group and beyond, where is our place in the larger scale structure of the universe, and then of course, how can we build an extragalactic distance scale that uses the Hubble-Lemaitre law to determine distances via the Hubble constant in a range where we can no longer use standard candles to measure this. So the Hubble constant, H0, is really an observed property that comes from the fact that the universe is expanding. the space in between all the galaxies is growing due to a cosmological evolution. And so as the space expands, what you observe in the nearby universe is an apparent relation between this apparent recession velocity v and the distance d. And that's really just because of the expansion of space. Now, of course, this is how the Hubble constant was initially defined, but we know that in a Friedmann-Lemaitre universe, it's a little bit more complicated, and we're really dealing with redshifts. Of course, redshift can exceed the unit value, so these are not Doppler shifts. This is really a cosmological redshift, and this Taylor expansion here includes also higher order terms of the redshift, where you have, for example, the accelerated expansion of the universe in this equation. So the Hubble constant is really a crucial number for cosmology because it gives an absolute scale to many cosmological inferences. It tells us about the critical density of the universe, and you can sort of think of it as one of the key constants of the universe. However, you can also think of of H0 as a cosmological end-to-end test that tests our understanding of cosmology, because we have the local universe, where we have stars and galaxies that we observe today, and we can use these to measure the Hubble constant. But we can also infer the value of H0 from observations of the very early universe. And here you see a portion of the temperature and isotropy maps from the Planck satellite that are then interpreted through the lens of a cosmological model, and in particular, the flat lambda CDM sort of standard or concordance cosmological model. So because I live in Switzerland, I like to use a metaphor that involves mountains. And in a way, it's almost like digging a tunnel from two ends of the mountain. And you're, of course, if your understanding of that mountain here, lambda CDM cosmology, were correct, then you would expect the two tunnels to meet up. But unfortunately, what we see is really a systematic difference of order 8% that currently exceeds already 5 sigma, depending on exactly which numbers you will put here. But the distance ladder I'll be telling you about comes out with a value of around 73 plus or minus unit kilometer per second per megaparsec, and the result based on the flat lambda CDM model applied to the Planck observations is at 67.4 plus or minus 0.5. So if we take all the measurements at face value, the big difference between these two tunnels we're digging is really the cosmological model. And so that motivates the statement that perhaps there is new physics that is not part of flat lambda CDM that needs to be considered in order to reconcile this. Because in a way, when we see a crisis developing of a model, then perhaps there's something new to be found. Now, some of you may have seen many presentations over the course of your careers on the Hubble constant. And so perhaps you might say, there's been tension in the Hubble constant since its beginning. And indeed, the Hubble constant does have a checkered past. It started out with numbers that were way too high, but eventually in the 1970s, in particular, there was this big fight, or the Hubble wars, between de Vaucouleurs and Sandage, somewhere between 50 and 100. Now, of course, we've kind of zeroed in on the middle of this. 73 is not too far from the mean of 50 and 70. But I posit that we're really dealing with a different problem. Now, you may have also seen this kind of plot in the past. There's a reason that I don't like this plot, but I just want to point it out because you will see it many times. This plot sort of seems to suggest that there's one measurement in the middle that will alleviate the tension between Cepheids and the CMB, but it's quite selective in that it only shows 3 measurements. This is by far not a complete set of measurements of the Hubble constant, but it's 2 years old, and I think the gist of it still holds. It's separated into indirect inferences of the Hubble constant that are always based on early universe observations that are interpreted somehow through cosmology, and then direct measurements that do not require explicit knowledge of a cosmological model. And these measurements are not all independent, so it would be very careful in terms of averaging over them, but some of them really are truly independent. You will see here, for example, the Rees et al. Or Schu's distance ladder based on Cepheids and type 1a supernovae that I'll be talking about today. This is completely independent of, let's say, the Maser value here, which, well, not entirely because it's one galaxy shared, but the systematics are really very different. And then another one that is worthwhile pointing out is here lensing related. It's these measurements that use the strong lensing of quasars and the time delay measurements in those systems to determine the Hubble constant. There are no shared systematics with the Cepheids and type 1a supernova distance ladder. Then, of course, maybe in the future, we will have more of these kilonovae gravitational wave events with electromagnetic counterparts that will allow us to do this kind of measurement. But the statistics for the time being are very limited with just one such object. Now, the thing I would like to really stress here is that all of the late universe direct measurements of the Hubble constant come out to one end of the early universe values. If these were just poorly understood measurement errors, we would expect scatter around the value coming from the CMB plus lambda CDM. But that's not at all what we're seeing. So already this tells you that there can't be too much of a problem here, even if some of the measurements lie a little bit closer. So if we now say that, fine, we believe the measurements and really there is a Hubble tension and we have to take it seriously, well, then what would be the possible solution for it? One is, of course, that the universe is not perfectly flat and it's not taken into account. So maybe there is some element of non-zero curvature. It can't be very large, that's well constrained, but adding curvature to the lambda CDM fit of the CMB does quite significantly affect these numbers. Perhaps it's also in the particle physics sector. Maybe it's something that GR is wrong or that the cosmological principle no longer holds perfectly. Or maybe there's something wrong with with the dark sector. I mean, if we look at the energy density today, this plot basically accepts ignorance over 96%, pardon, 95% of the majority of the universe. We do not know the particle type of dark matter. We only have indirect evidence for it. And we don't have a good theoretical understanding of dark energy. So I would say that hopefully this is the goal or this is the path to learning something new. I'm not claiming I have the answer. One of the more successful models that have been explored has to do with an early dark energy, but for the time being, there is no very clean solution. So there's a lot of efforts, of course, on the cosmology side to explore this and other tensions. And there's a cost action specifically targeting tensions in cosmology, such as this one, and also the sigma 8 tension and any other tensions that could potentially indicate new ways by which to modify cosmology. And if you're interested in this sort of cost action, it can be very useful. Please feel free to follow that link. We're doing networking events, short mission stays, and schools and so on, in an effort to do really inclusively cosmology within Europe. So then how do we actually go and measure the Hubble constant using this distance ladder? Well, you may have seen this plot from the SHOES collaboration that has these 3 beautiful panels, and there are 2 types of standard candles on these 3 rungs. And I'll start at the farthest out rung, and that's because this is the realm where the universe should be isotropically expanding. So that's the so-called Hubble flow. We're somewhere in the range of 90 to 600 megaparsecs or so. This is where the motion of galaxies should not be dominated by peculiar motions, so that their gravitational attraction. And in order to measure that Hubble flow, you really need extremely luminous objects, and the type 1a supernovae are exactly those kinds of objects. They're extremely luminous, they outshine entire galaxies, but unfortunately, they're very rare within a given volume. So that's why we need an additional type of standard candle, in this case, the classical Cepheids, in order to provide the absolute calibration to the supernovae, which are very precise relative distance indicators, but require this external calibration since we don't have them observed in a galaxy to which we know the distance through geometric means. So we end up with this sample here of 42 type 1a supernovae and 37 type 1 galaxies where Cepheids have been observed. All of this has been done on the Hubble Space Telescope. So there's a unique and homogeneous photometric system on which this is all done. Nowadays, of course, there's also the James Webb Space Telescope that has started to contribute to this. There's already several galaxies that have been observed, and I'll actually be showing some of those results. Now, in order to measure the distances to the Type 1a supernovae, we use the Leavitt law, named after Henrietta Leavitt, who identified this relationship between the logarithm of the period of the Cepheids and their intrinsic luminosity. You can measure the average period from the light curves, and then by measuring Cepheids, for example, using Gaia parallaxes, or in the Large Magellanic Cloud, where the Araucaria project has measured the geometric distance using detached eclipsing binaries. Also, very recently, the SMC has been added. That was just last week. And NGC 4258 is a water megamaser galaxy to which a geometric distance is known. So in this realm here is where you calibrate the Leavitt law, which then in turn sets up the absolute scale for the entire distance ladder. So in some sense, you can think of this as the standard candles linking the supernovae to geometry. It's the geometric distances that we really want as the absolute scale. Everything else is done differentially using flux comparisons, and the supernovae map out the flow of the galaxies. So in my group, the project name that I came up with for what we're doing is HIPSTERS, or measuring Hubble's constant to 1% pulsating stars. We're pursuing a three-prong approach to measuring the Hubble constant. And in this case, what we're really striving for is accuracy. We want to make sure that this 1% measurement is, of course, precise as possible, but also we need to make sure that it's close to the truth, and that requires ruthless analysis of systematics. And so that's really what we're spending most of the time on, while, of course, also trying to reduce the dispersion of the measurement. And in addition to that, we want to further the understanding of pulsating stars, because I'm interested in stars in the first place, but also because I think that is the path forward to identifying further systematics and improvements to this distance ladder. So in the next little while, I'll tell you a few of the highlights that we've been able to come up with so far. They have to do with understanding the parallax accuracy that we can have for Cepheids, for example, using astrometric means, asteroseismic means, how we can calibrate the Leavitt law on an absolute scale using Gaia. Also, I will tell you about the James Webb Space Telescope measurements of Cepheids, and I'll also tell you about a different type of stellar standard candle, the tip of the red giant branch. So let's start with Gaia and how it helps us anchor the base of this distance ladder. As you may know, when you're looking at the sample of quasars in Gaia, you can construct this sort of all-sky map, and this is the plot here from the Gaia collaboration by Lindegren in 2021. And unfortunately, there's quite a lot of correlation in the parallaxes that you get from quasars across the sky. That's, of course, surprising, because a quasar should have 0 parallax on average, although, of course, the measurements can scatter plus or minus according to their uncertainties. But overall, you find a total offset to this entire sample of quasars of about 17 microarcseconds. That's really unfortunate for Cepheids, because that amounts to a 10% systematic error at a distance of 5 kiloparsecs, which is sort of the realm in which we want to calibrate the Cepheids. So we need to understand this parallax systematic much better. And one way that we did this is by asteroseismology of red giant stars. And my postdoc, Sanya Khan, who's senior at the top right, has had 2 papers on this last year, where in the first paper, she focused on the measurement of distances to more than 12,000 red giant stars from TESS, Kepler, and K2, because when you observe the frequency patterns of these stars, you can basically do an inversion that uses stellar models together with spectroscopy and photometry, and predicts the bolometric luminosity, which in turn you can turn into parallax measurements. So it's a stellar model dependent parallax that we can then compare to Gaia. Now, in the second paper, we focused specifically on 3,500 red clump giants, because they form the most homogeneous and similar data set among the different fields that we were able to study. And so we considered that best for the parallax offset determination. And just to let you know, the systematics of these comparisons are of order 5 to 10 microarcseconds. And overall, we get a very patchy but where we have it, quite dense coverage for relatively bright stars. And this is important because, in particular, the magnitude range where we want to calibrate Cepheids, that tends to be much brighter than where the best calibration of the parallax offsets in Gaia have been achieved. So if we then compare the Gaia EDR3 parallaxes to our asteroseismic parallaxes as a function of magnitude, this is in the Kepler field, and if we bin then the results as a function of magnitude, we see some quite curious patterns here as a function of magnitude. Once the corrections that have been published by the Gaia collaboration are applied, we see that this systematic trend as a function of magnitude nicely flattens out and actually approaches zero offset. However, at the bright end, the stars tend to move towards a positive difference in parallax. So it looks like the parallax comparison that we're showing here suggests that at the bright end, the corrections that have been determined so far using bright physical pairs by Lindegren et al., they overcorrect the effect, but they do a very good job at something like 11th magnitude and fainter, and in particular to remove these systematics. If we then take a more bird's eye view of other kinds of studies that have been done to this effect, initially, there was some reports that maybe there was a residual in magnitude, because if we can ignore this blue line and this purple point, then this is highly suggestive of some sort of magnitude dependent trend. But I'd like to pull your attention to these shaded regions here. The pink is what I showed you here on the left. Yellow is K2, which has poor frequency resolution for the astrometry, unfortunately, and is also well, because the baselines over which the asteroseismology could be determined is much shorter. But this over here is TESS, which actually has, in the southern continuous viewing zone, a 1-year coverage. So essentially what we're seeing between these three regions is that using the same methodology, we get very different answers for the parallax residuals that suggest that there is a sky dependence, so kind of a position related dependence that is not fully accounted for among the bright stars. So bottom line is then we should use stars that are fainter than 11th magnitude or so in order to get to the best results. And of course, we have to be vigilant to ensure that the parallax corrections that we use are accurate. So in order to get the best calibration of the Milky Way Leavitt law, we then used star clusters to do this particular work. And the idea was basically that if we're looking at, so Cepheids are relatively young objects, sort of between 30 and 300 or 600 million years, depending on the period. So they occasionally occur in clusters. And in the Milky Way, it's about 10% or so of the Cepheids that occur in clusters. So what we did was we started at the position of all the Cepheids that are known in the Milky Way, and then we searched for clusters that are associated with these stars using a 6-dimensional cluster membership analysis. And it turns out that in particular, proper motion is able to distinguish between the gravitationally bound clusters and the field star populations. This allowed us to detect 34 Cepheids that belong to 28 open clusters, and we were able to measure a typical cluster parallax of about plus or minus 7 micro-arc seconds. So that's the typical uncertainty that we get. And this is really driven by two things. One, of course, we're averaging over many stars, so we can beat down on the statistical uncertainty. And two, we're dealing with stars that are really fainter than 11, usually fainter than 12th magnitude. And so we're in that range where the parallax offset corrections are best informed in Gaia. At such a small uncertainty, we're looking at something like 3 times smaller uncertainties than for a field Cepheid. It means that one Cepheid in a cluster carries about 9 times the weight as a Cepheid in the field. So if we're looking at the right-hand side here, this is the absolute magnitude in this funky Wesenheit formalism that is used by the Shoes team to measure distances. Happy to tell you more about this, but this is a reddening free magnitude as a function of period. we can compare the gray points. These are the field Cepheids, where you have the individual Cepheid parallaxes, compared to the cluster Cepheids in red. And here's just the residual. You see immediately that the clusters have much, much smaller scatter. That is just a testament to their intrinsic accuracy. And actually here, this dispersion of 0.07 magnitudes, that's about the same as you have in the LMC. So thanks to the cluster Cepheids, we're able to get to the same precision on the Leavitt law as otherwise you would get in the LMC. Combining this constraint with the Schu's distance ladder allowed to improve the uncertainty by about 7%, down to less than 1 kilometer per second per megaparsec, and ended up increasing the tension because it didn't really move the Hubble constant value that much, but improved the accuracy on the measurement. And going forward with Gaia DR4, we expect to do much better because proper motion constraints become really better when you double the baseline of the measurement. So we'll be able to identify much more of these Cepheids in clusters that will carry such high weight in the calibration. So if we then move to the second run, where of course, this is where we have the galaxies that host both Cepheids and Type 1a supernovae. Nowadays, James Webb Space Telescope is, of course, the new kid on the block and boasts extremely good precision thanks to the large mirror, especially in the infrared, but also has much better spatial resolution than HST had. And so people have been very keen on applying James Webb to supernova host galaxies to remeasure the Cepheids. And in particular, because one of the sort of concerns people had about the Schu's H0 measurement is illustrated here in this comparison of these spatial footprints around a Cepheid. So the position of the Cepheid you see here as this red circle with the star inside. And in HST, you see right away that the spatial resolution is about a factor of 4 poorer than in James Webb. So in the optical with HST, you have roughly the same spatial resolution as in James Webb. The identification of the Cepheid was not really a problem. That worked just fine. But in the HST imagery, you needed to somehow correct statistically for the amount of blending that sort of enters your PSF measurement of the Cepheids photometry. And so people would then make reference to this as a crowding bias, in the sense that if the statistical correction for the extra flux is not accurate, then maybe that would bias the overall distance ladder, because as you go to greater and greater distance, that crowding bias would become more important, and that would essentially mimic an effect on the Hubble constant. So this has now been measured in NGC 4258, which is a host galaxy, as well as an anchor galaxy with a geometric distance, and 5 Type 1a supernova host galaxies. And I'm just showing 2 examples here. The others are in the paper by Rees et al., where you see the gray points. Those are the photometric measurements from HST, and in red are the measurements based on James Webb. So the photometric systems here are essentially the same or very close to one another, can be transformed extremely accurately. And the improvement in the dispersion by a factor of 2.5 is really given by this improvement in the spatial resolution. That's because the artificial star tests have to remove much less crowding flux. And so the uncertainty associated with that correction is smaller. In addition, the signal to noise on the Cepheids photometry is also higher in James Webb because of the larger aperture. So this is really a very significant improvement in the PL residual. However, then when it's applied to all the galaxies that we have, the anchor galaxy here, NGC 4258, and the 5 supernova hosts, we see that there's a perfectly flat residual between James Webb and HST and the distances of these galaxies. And of course, if crowding bias had been a problem, then you would expect more and more crowding as you go to greater distances, shown here by this dashed dotted line. And by having measured this now with these galaxies, the crowding bias is excluded or rejected as an explanation for the Hubble constant tension at a significance of more than 8 sigma. So that test of crowding is even more telling than the Hubble constant tension itself. If we now go to an alternative calibration of the distance ladder using the tip of the red giant branch. This is quite interesting because there's been some reports that using the tip of the red giant branch could, on the one hand, be possibly a better measurement of the distance ladder, and also that this measurement would be consistent with the Planck result with flat lambda CDM. So earlier this year, the paper was published, but we started this project about 2 years ago with an undergraduate student, Nolan Kublischke, who's now a graduate student at the University of Toronto. And we actually ended up looking at OGLE data of the Large Magellanic Cloud. And then specifically, I was interested to know what can variability tell us about this TRGB measurement. So for those who are not familiar with the tip of the red giant branch as a standard candle, it's a statistical feature in this color magnitude diagram. So here we have the D-reddened I-band magnitude, D-reddened using the OGLE-4 extinction maps of the Magellanic system, and then here the D-reddened V-I color. The density contour here just shows where the majority of the stars are located, so the red giant branch is nicely visible. And then you see how it sort of disappears here, and that's the TRGB as an empirical feature. Astrophysically, this is the telltale sign of the helium flash in first ascent red giants. So if you can recover the same feature in another galaxy, you're in business for measuring distances. But what we did here is we considered the catalog of long period variables published by Igor Sozinski, and we found, to our surprise, that as you go up the red giant branch, all of the stars become LPVs. So the color coding here is the fraction of small amplitude red giants from this LPV catalog that are per color magnitude bin here. So we're really approaching 100%. You see this also here in the luminosity function shown on the right. The dark gray line is the overall luminosity function. The yellow line are the small amplitude red giants, and then the gray is just the complement. So at the TRGB, 100% of stars are measurably variable, and in addition to that, multi-periodic pulsating stars as per the OGLE catalog of variables. So what's really interesting then is in these long period variables, we have multiple PL sequences, and that has been known since the late 90s. And what we did was to distinguish now between the two most populated such sequences, and specifically the so-called sequence A and the sequence B. And we then just applied the same methodology for measuring tip, which is a so-called Sobel filter. So we're looking for the inflection point of the luminosity function for these two variability selected samples. And what we found is really that the A sequence in yellow gives a fainter result than the B sequence in red. This is really peculiar because overall, these stars, together with all the other LPVs, they make up the overall population of red giants, right? That you use to calibrate the TRGB. But now we can do a variability selection that gives us systematically different answers here at about 5 sigma difference between these two measurements. And that raises an important question, because as we go to more distant galaxies and we try to measure the same thing here in NGC 4526, the question is really, which of these measurements should we adopt as our base calibration? Because the distance will be essentially, when we take this apparent magnitude, we shift it to an absolute magnitude known using the known distance of the LMC. But then which of these calibrations should we use for the absolute magnitude? And if we don't know, then that means that there's a systematic uncertainty of 2% that applies to all of these distances. In addition, we don't know the makeup of the red giant branch population in this galaxy, because halos of galaxies can have a long past of mergers, of star formation, and so on. And we don't necessarily know exactly how every galaxy is made up. And we have very limited observational means for figuring that out. So it turns out that these two sequences are also an evolutionary sequence where the A stars or A sequence stars are younger than the B sequence stars. So presumably, if we're dealing with really old red giants in the halos of these other galaxies, then we should probably use the B sequence calibration. However, that would have to be verified with some additional information at the more distant galaxies. So we're of course also then interested in cross-checking our distances, because there is this debate over whether the TRGB or the Cepheids should be trusted more, and so sometimes it helps then to have a third arbitrator or a referee that sort of tells us what is really the accurate thing to do. So in this particular case, I teamed up with a PhD student from the Max Planck Institute for Astrophysics in Munich, and we measured the distance to M51, here this beautiful interacting galaxy and this red part of the galaxy, using already published photometry. This was the first Cepheid-based distance estimate to that galaxy. But Geza is also an expert in type 2P supernovae explosions using the so-called expanding photosphere method. That's, if you will, a kind of a Bade-Wesselink analysis applied to supernovae. And that gives a direct measurement of distance that does not require a calibration using, for example, Gaia, because it actually just measures the spectra, performs radiation transport of the spectra, and measures the brightness of the stars to then infer the overall luminosity. And so the type 2P supernova distance is shown here in green, and the Cepheid distance is shown here in red. And this compares in accuracy, actually, both are very consistent with one another. They're completely independent measurements, but they don't agree with the TRGB measurement that has been previously published to that same galaxy. So if we look here in the yellow, this is the field that was chosen for the TRGB measurement at the time. And as we can see, well, there's really, this field falls onto a spiral arm where there's, of course, high source density, there's star formation, there could be young stars in there. So there's a few things that apply to this field and the population of red giants that probably are not optimal for measuring TRGB distances. However, it's kind of difficult to know that if you're just looking in a catalog of galaxies, right? If you just consider any distance to a galaxy and it says, oh, it's a TRGB distance, you would have to go really deep to start to understand why a galaxy distance may be biased. So I think this kind of work is very important to understand really the accuracy of the different methods and also the reliability of the distances that are published. And if you will, I would sort of draw a broad distinction here between distances of Cepheids and the TRGB. And that's that Cepheids and other pulsating stars are individual standard candles. That doesn't mean that they all have the same luminosity. Of course they do not. This is the Leavitt law that shows you how period changes the luminosity very clearly. But you can measure each of these stars individually with its parallax in the Milky Way and its flux. And if you know that Leavitt law and you measure the period, then you also have an individual distance with just a single Cepheid. So that is a very powerful tool. On the other hand, the tip of the red giant branch is a statistical method in that you need an entire population to measure the distance, and that opens up issues such as this diversity of red giant populations I was telling you about. So I think we really need to do a lot of work to understand these problems of the diversity that have to do sort of with age and with metallicity primarily in order to understand this better. And we have some work going on in the SMC that will help us elucidate this more. So the gist of everything I told you about what this work on the Hubble constant is that we've really worked to improve the distance scale. We worked to improve the absolute calibration and the calibration of the supernovae. I personally have not touched the supernova part of the distance ladder myself. But these two elements, really the first and second rung of the distance ladder, are the rate limiting steps for H0 accuracy. And as we've been touching and improving on this, what has come out is that the tension has grown. The base value of the Hubble constant tends to move a little bit up and down, but the uncertainties tend to shrink, and that ends up increasing this tension with lambda CDM. So from my perspective, there's currently no direct H0 measurement that really contradicts the Cepheid and supernova host distance ladder. And the ball would then be in the court of the cosmologists to tell us how the universe is telling us something new. There's a whole book that's going to come out in June this year. It's called The Hubble Constant Tension, and it's edited by Eleonora Di Valentino and Dylan Brout. Eleonora is an expert on cosmology, and Dylan Brout has led the cosmological analysis of the Pantheon Plus supernova sample. I personally contributed the chapter on Cepheids, but this will really have a very comprehensive view on many of these issues that are behind the Hubble constant tension. So if you'd like to know more, have a look out for this book. I think most of the articles that are in the book are already on the archive. So now that I still have a little bit of time left, I'd like to shift gears completely and tell you about something that I'm very excited about with respect to classical Cepheids, because I've been doing radial velocity measurements of Cepheids since my days as a PhD student when I was visiting Warsaw Observatory the last time. I think that's maybe 12 years ago or so. We've recently had well, basically, we're in the process of doing a big data release that I'm very excited about. And so this is the Veloce project. Veloce is Italian and means fast. It also stands for velocities of Cepheids. And we see up here the three contributors, besides myself, that are really driving this work. So Giordano Viviani here seemed very happy that finally all his work is going to get published. Then Shreya Shetty and Henia Netzel, who joined the team last year. So the data release, as I mentioned, is imminent right now. The paper is already on the archive and is in publication right now. It's the largest catalog of Cepheid radial velocity time series with more than 18,000 observations. That's even more than are in the Gaia Cepheid radial velocity time series catalog of 258 Cepheids. So the number of Cepheids is smaller than Gaia, but the number of observations per Cepheid are larger. We have a median of 57 observations per Cepheid, and we have really observations from both hemispheres. You see here the Euler telescope at the Swiss telescope here in La Silla, and we also use the Mercator telescope on the island of La Palma with the Hermes spectrograph. And with these two spectrographs, we really get unprecedented precision for the radial velocity measurements of Cepheids, as good as 2 meters per second with Coralie for very bright objects. More typical is 50, but the median over the overall survey is 37 meters per second. We have very good phase coverage and up to 12-year baselines to also study binaries, for example. So think of this survey as a legacy reference of precise radial velocity curves that allows to tie in old data as well as future data. In particular, something we've spent quite some time on is the Gaia RVS measurements, but we also have a companion paper currently under review on a systematic study of binaries. And Henia Netzel recently had a paper accepted where we show that these data also allow us to identify non-radial pulsations in Cepheids that have otherwise been identified, or similar pulsation features have been identified with tests in Cepheids. Some of the things I'd like to point out here is, for example, this classical view of Cepheid pulsations called the Hertzsprung progression, which identifies a bump feature that sets on somewhere around here at 6 or 7 days, and then moves to shorter and shorter phase as you go to longer periods. Now, all of these curves I'm showing you here on the left are first overtone Cepheids, on the right are fundamental modes. All of these curves are the fitted Fourier series models that we have for these data, otherwise you wouldn't be able to read the plot. But if we zoom in here at this region, we can actually see that many of these models exhibit double bump features that were not previously known. This first bump is assigned to a resonance between overtone modes. So presumably this double bump feature is a similar telltale. And just to convince you that this is not a problem of sampling, here is the phase folded radial velocity curve overplotted for one such star. So the detection of this double feature is really very significant, and it's really enabled by the precision of the measurements as well as the dense phase coverage. So hopefully this will tell us something more about the structure of Cepheids. Among the spectroscopic binaries, we have about 76 of them in Veloce. We have very good orbital as well as pulsation phase coverage. Here we see Delta Cepheid. That's the prototype of the classical Cepheids. In 2015, I was able to show with just a subset, I believe it started around here and went until here, that the star is a spectroscopic binary. But because of the limited baseline of the measurements at the time, unfortunately, the orbit was not quite correct. There was about a factor of 2/3 too short. So now that we have sampled the full orbit, we can of course correct that orbital period. And that was actually recently confirmed also by Nicolas Nardetto et al. In an ANA letter. We overall have 34 fully solved orbits based on mostly Veloce data, as well as some literature data, especially if we have very long orbits. They go to several tens of years in some cases. And so we're really getting a first view of the overall population of orbits in Cepheids. Here we see this characteristic growth of eccentricity, for example, as you go to longer orbital periods. And this is quite interesting because it tells you, for example, about the birth environments of Cepheids and the kind of dynamical interactions that they could have had in their clusters. And we have some work with an N-body simulation specialist to look exactly at those things. As I mentioned, we have compared Veloce quite extensively to Gaia RVS measurements. And as we did this, we were, of course, interested in just seeing whether the mean velocity of the Cepheids would be the same in Gaia and Veloce. So here you see the difference on the y-axis. Maybe can I get the... I'm just looking if I can get a laser pointer going. Okay, I don't know how, so I'll skip this part. But I hope that you can see my cursor. Basically, this difference here is the difference between the published gamma velocity in Gaia and then the one that we infer from Veloce. And we see an overall mean offset for these stars of about 650 meters per second. That's not too surprising. That's totally within the range of what you have also for other data sets. But what was surprising is the large degree of scatter between these mean velocities published in Gaia. And so we looked a bit deeper into this, and it turns out that this is linked with the template parameters that Gaia uses to measure the radial velocities. And so here, this is a plot of the difference, again, between V gamma in Gaia and Veloce. In orange, we've highlighted stars that are within, let's say, a reasonable range of temperature parameters for Cepheids. Sometimes Gaia adopted very low metallicity things or really too cold or too hot. And it turns out that if you're looking at just the ones that are in the right ballpark, the scatter reduces quite substantially. So that leads us to say that when you're considering a specific population of stars like classical Cepheids that are kind of intrinsically one group, it would make sense to treat them all with the same template parameters to ensure consistency and the ability to compare the measurements very well. There's a whole zoo of modulated phenomena that we see. For example, in 2016 already, I was able to show that the line shape variations do not repeat very well from one cycle to the next. That's indicative of probably coupling between the pulsations and the convection. As I mentioned earlier, Henya Netzel recently had this paper accepted that shows that we have here in this Peterson diagram, where you see the ratio between two periods measured in the cross-correlation profiles of the Cepheids as a function of period. You see the four Cepheids for which we have these detections, and they follow these ridges, L7, L8, and L9 for the 0.61 Cepheids, for which there is already a theoretical explanation by Jimbowski, as well as here these 0.68 stars that have been identified also in the LMC, but that do not yet have a theoretical explanation. And currently, we're looking also at line splitting patterns. Here, for example, you see a star where you have very significant line splitting phenomena that are probably also indicative of similar effects. So if I still have a few minutes, I'd like to shift gears again and tell you about how going forward, we want to measure a lot of spectroscopy of variable stars and other time-resolved features using the Wide Field Spectroscopic Telescope. Here's the website, wsttelescope.com, if you'd like to learn more about this. This is essentially a future facility that we're currently developing as a concept study, and we're hoping, of course, there's no guarantee whatsoever at this time, but we're hoping to make this a future ESO project after the ELT. So what we're dealing with is a 12-meter diameter telescope built of 78 segments with an area covering about 99 square meters. And this telescope you can think of it as a spectroscopic counterpart to LSST. The idea really is to have this massive focal plane in order to go very deep, but at the same time to build an optical system that is able to observe very large areas of the sky. So the area here would be 3.1 square degrees in the current setup. And in this very wide 3 square degree field, you would have 20,000 low resolution fibers patrolling in addition to 2,000 high resolution fibers. And then in the center of this very wide field, you would have an integral field spectrograph that is 9 times the area of MUs, so 3 by 3 arc minute squared, that can patrol within a 9 by 9 square arc minute area. So can mosaic, for example, while the multi-object spectrograph is working at the same time. So this is, of course, a very large facility. So we've been collecting community support in various working groups, including a galactic, extragalactic, cosmology, and time domain working groups. I particularly lead the time domain working group. And if you'd like to get involved, then please go visit wsttelescope.com. There's a sign-up link that allows you to join the science groups. For example, if you're interested in stars and things like the Magellanic Clouds, and the Galactic Working Group is, of course, for you, but because we're also in the time domain very interested in variable stars, I would very much encourage you to also join the time domain if you're interested in this. And to learn more, please also have a look at the white paper that we published earlier on the archive this March. So just to give you a sense of the top level requirements we're seeing right now, so the low resolution would be of order 3 to 4,000. The high resolution would be 40,000. We're really trying to do a factor 2 better than foremost in this particular case. And then the IFS resolution would be about 3,500. This would be all in the optical, sort of between 350 and 370 nanometers, depending on the instrument. But what's very interesting is that we're gunning for really simultaneous measurements of the multi-object spectrograph and the integral field spectrograph. And so, for example, for resolved galaxies, this will be fantastic, where you can map out the cores of these galaxies with the IFS and then measure objects in the vicinity using the multi-object spectrograph. And we're already considering an IR upgrade in the future, so the telescope itself should be sensitive in the infrared, even if for cost purposes, we cannot currently consider infrared detectors. And we're also really building into this from the start a kind of time domain mindset in order to get time resolved measurements. And that will notably include telescope level target of opportunity observations with lead times of 12 to 24 hours and fiber level TOOs that just wouldn't change the pointing of the telescope, but reallocate different fibers within relatively short timescales before the beginning of the night. And so within the time domain, we're really covering a very broad array of science cases, all the way from solar system comets and exocomets to all types of stellar variability. Notably, white dwarfs are of extreme interest with this kind of facility because it's such a large collecting area that you can do a lot of interesting things. But also the Magellanic Cloud with WST will be fantastic laboratories for getting high resolution spectroscopy. Then, of course, we have the classical transients like stellar flares or supernovae, CVs, tidal disruption events, and so on. And we have quite a bit of an effort going on to link spectroscopy with gravitational wave events from the Einstein telescope or Cosmic Explorer in the future. So really there will be, because we will have multiple epochs at every pointing, there's really the possibility to have alerts at any wavelength. And I think this is particularly exciting because it opens a serendipitous discovery space that is currently not otherwise available. So thanks very much for your attention. I'd like to first off shout out all the wonderful people that I have the pleasure of working with every day, and just summarize very briefly. We have made very good progress on the distance ladder, both in terms of its accuracy and its precision. And as we've been doing so, the Hubble constant tension has been growing. And that, of course, puts the ball in the court of the cosmologists to tell us what's going wrong. In particular, James Webb has now confirmed the HST results from the SHOES team albeit with improved precision. So that's really great. On the one hand, it improves the overall distance ladder, but on the other hand, it tells us that at least the poor resolution of HST was not to blame for the tension. We're also slowly clarifying the systematics of the much newer TRGB method for distance determination. There are many other systematics we've looked at that are really part of the methodology that are more of an algorithmic kind. I'm happy to tell you more about that if you're interested. However, despite this tension growing, it's curious that there's no viable solution from theory at this moment. It's not for lack or for want of people trying. People are trying to break GR, coming up with early dark energy, modifying all parts of cosmology. There's probably over 1,000 papers already of cosmologists trying to solve this issue, and no solution has been found for the moment. So we'll see what comes out at the end. And if you're interested in Cepheid radial velocities, I encourage you to have a look at Veloce. This really is an unprecedented set of Cepheid RVs. And if you're interested in large spectroscopic surveys and want to contribute to something that is sort of towards the end of the 2030s, then please talk to me or get in touch for WST. Thanks very much for your attention.
Thank you very much. Thank you, Richard. Questions from the audience here? Milena.
Can I see from here, or should I?
Well, you can better come over.
Good afternoon, Richard. It's Milena. I hope you can hear me. Thanks for the presentation. I was actually wondering, in a comparison of Veloce and Gaia radial velocities, you said about this scatter, right? And
yep.
You said the reason for that is templates that Gaia uses for radial velocity. But I mean, Gaia's radial velocities are just calculated based on a calcium triplet, right? So at the very, very short range of spectra. So I mean, isn't that the reason? I mean,
so it's true that the different lines that are used by Gaia compared to what we have here is an area of concern, and I was initially more concerned about it than I am now. It's true if you look at the radial velocity curves, what you'll see more is changes in the amplitude because the curve shape looks different. But when you're comparing the mean velocities, it's a little bit different because that's intrinsically less sensitive to the differences than the amplitudes. We also have a comparison with amplitudes that I don't have here in the presentation. I think that is currently limited by the number of epochs available from Gaia. But the detailed comparison of the RV curves does show that, in particular, at the steep end of the radial velocity curve, there are quite some differences. So with part of the sample that we have here, because Hermes actually, in the northern hemisphere, that spectrograph is sensitive in the calcium triplet, we're going to look at the very direct comparison with Gaia and Veloce in the same range of wavelength. Another difference is, of course, also the spectral resolution. Gaia RVS is about 11,000, Hermes is 85,000, Coralie is about 50,000. So there are some systematic differences. I think everybody who wants to work with things that are sensitive to amplitudes, like Bader-Wesselink analyses, really have to be careful about these sort of effects at the moment. But for mean velocities, I think this is, that's the comparison.
Thanks.
Do you think this problem will be less an issue with DR4 and then DR5 when the longer time series from Gaia are available?
So absolutely. I think, as you can sort of see here on the right-hand side, this panel here shows the number of observations. You will regress more and more towards a common mean as you have more measurements. So in essence, I think the main differences you would have then between Veloce and Gaia would be down to things that have to do with the line shapes that can be a worry at the level of a kilometer per second or so. That, of course, won't change anything about the intrinsic shape of the RV curves measured using different lines. I really do hope that going forward, specific variability classes can be treated using a single set of correlation parameters so that everything is more consistent with respect to one another. Here, we're really dealing with too many differences at the same time. But this, we're working to simplify this matter in the future. But I think this is probably best done at the CU level.
Okay. Any more questions? Mariusz? Come forward.
Hello, I have a more economical question. What will be the WST project timeline and costs?
Yes, so cost is, of course, an interesting question. So we published that white paper in support of a funding proposal that we submitted to the EU. That funding proposal should help us get a concept study funded to really make this project much more concrete and really develop the top level requirements and so on, and build, sort of come up with a project that we want to sell. At the moment, our cost envelope is at 800 million euros. So that's why we're really hoping to make this a future ESO facility, because we wouldn't see another entity being able to fund such a kind of project. But mind you that this is answering in some sense a call from the ESO community, because there was a survey done by ESO asking for what would be the most useful infrastructure that ESO should build for the overall community. And by far the most requested one that is not yet already being built or planned was such a type of facility. Really a dedicated spectroscopic telescope with a wide field of view that can observe many, many objects. So we're really, of course, this is an expensive project, but we're answering also a call that is there in the community. And I think it will be really transformative then, especially in comparison or in conjunction with LSST that would provide the imaging at the same time.
Yeah, but I think that the primary
timescale
is finished when WST appears.
So it's true that the first, I failed to answer your question about timescale. Timescale here is end of 2030s or so. I think that's reasonable for such a large project. It's true that the first phase of LSST will be done at that point. But I recently spoke to Željko Ivezic, the project scientist for LSST, and he actually said that if ESO were to build such a facility, then that would change, or that would have a very significant impact on the long-term plans for LSST, because LSST currently was considering possibly going spectroscopic in the future. But of course, if there is a spectroscopic facility that can do this, then there's no need to do so. And so they would look at this with a very interested view and maximize synergies. And I don't think that LSST will just, the Rubin Observatory will not just be demolished after 10 years.
I think so. And site will be parallel.
So the site that we have in mind would be a third site. It wouldn't be Cerro Paranal and also not Arbasones, but a third site that's a few kilometers away from them, so that we can benefit from the solar power plants and from the control rooms at Paranal, but it wouldn't be the same mountain.
And how does this compare to WEAVE on La Palma, on Herschel?
I don't know all the numbers of WEAVE by hand, but the WEAVE is on a 4-meter telescope, and this is 12. So it's very significantly deeper. It has about, can you remind me the number of fibers on WEAVE? Is it 1,500? 2,000?
It's about 1,000, I think.
Oh, yeah, I think WEAVE is about 1,000. So this would be 20,000 low resolution fibers and 2,000 high res fibers. So it's a, plus, I mean, the integral field spectrograph at the center is 9 times the area of MUSE, which is currently the largest integral field spectrograph available. So we're really looking for very substantial improvements over the current infrastructure, because I don't think that otherwise we could justify such an expense. And we're really looking for the most exciting science cases to justify building it. So, and also to define the top level requirements. In other words, if you're into that sort of thing, we're really looking forward to your contributions to this as well. Things are really in an early stage, so it's a great time to get involved. Of course, we don't know if it's going to happen, but we certainly hope so.
I think it's a great idea, and the overlap with LSST, at least in terms of the hemisphere and the depth, is something unique, and it moves the science forward, I guess. Okay, I don't see any more questions. There's no questions on Zoom, so let's stop here and let's thank our speaker again. Thank you, Richard, and thank you all for joining, and goodbye.
Thanks very much.